Alright, boys and girls, welcome back to the drive-thru for a remix. Alright, we're giving this another shot. Trying to explain, this is a lot of stuff, so this is going to be a long video, I think one way or another, but we're going to give this another crack. Projectile motion. It's motion that's of any object that gets launched. So we're going to launch things at determined angles. So what you're going to, and these vectors are going to really have two variables. What angle do we launch them at, and what velocity do we launch them at? Okay? Well, we're going to break up that velocity vector into two different components. So we're going to be using a lot of trig and a lot of vectors. So you're going to tap into some other things that you've done before. Okay? I'm just kind of going through this PDF. The PDF is linked to Schoology. So some things that we're assuming is that, well, acceleration is constant. So that's important because as you get further and further away from the Earth, into closer to outer space, further into the atmosphere, acceleration may change just a little bit. But we're going to not take that into account for now. We are also going to completely ignore the effect of air friction. Okay? So, you know, you can think about air friction as when a material provides drag due to the air, then it slows that object down and changes its path. So maybe instead of having a completely parabolic path, these are going to be R objects. The actual objects might move more similar to something like this because of what friction does to it. But it's going to give us a good enough idea so that when we get into higher level physics, we'll be able to figure this out. That's kind of the goal of this. We're going to figure this out later when we get older. Okay? I really like this. What this is explaining what happens to velocity throughout a projectile's life. So notice that in this particular scenario, the velocity in the x direction, the horizontal velocity, it never changes. It is the same throughout this picture. And you'll notice that the velocity in the y direction does change throughout the picture. It changes both in terms of direction and in terms of size. Here it's going up and it's big, it's up and it's medium. Here it's gone, it's zero. Here it's going down and it's small or medium, and now it's down and it's big again. Well, that's because gravity, which is illuminated by that vector, is always pointing directly straight down. So if you think about something as it's launched in the air, when it reaches its peak, the vertex of it, its vertical velocity is zero. It is neither traveling up nor down. It stands still from a vertical standpoint for some small amount of time. Okay, we're going to really use this, although for what we're going to use, really this is going to be gone a lot. So what I just erased there, that was our initial position. We conveniently just put ourselves so that we start at 0, 0 in this particular video so that you can understand the rest. And then what I'd like to do here is talk about the initial velocity, talk about this right over here. If we launch something at some angle, at some initial velocity, then if we wanted to break it up into components and call this v sub x, Well, let's change color. And v sub y, well then we would just use cosine and sine, just like we did. So if we wanted to write that vector, it's the magnitude of the velocity times the cosine of theta, the magnitude of the velocity times the sine of theta. And hopefully you guys recognize that. Okay, I really like this. If we shoot something off at this initial velocity, then why does it travel in that path? Why doesn't it travel in this path? Well, the answer is because of gravity. Okay? Keep in mind, remember, our initial velocity is 0, 0. Sorry, our initial position is 0, 0. And then we're going to take our initial velocity vector and multiply it by time. But the thing is, if you remember, gravity is negative 9.8 meters per second squared, where gravity is negative 32 feet per second squared. Okay? So this really is always represented by a downward facing velocity, and so that's what's happening. If you think about this point right here, since a longer t has taken place, then gravity has had more time to have an effect on the item. So like every single point on our position is the combination of our initial velocity minus the effect that gravity's had. So that's just I thought, a good mathematical way to understand the science behind this. Alright, now let's get at this tough problem. We've got 3 objects launched, 30 degree, 45 degree, and a 60 degree angle. Which goes the highest, which goes the furthest? Notice they're not asking for any specific answers here, so I'm just going to answer this question. This is where my last video went so bad. But let's take a look at this. Let's just look at example 1, the 30 degree example. So, we launched something at 100 miles per hour. Is that what it said? 100 meters per second, excuse me, at a 30 degree angle. Well, if we break that up into the components, we're going to use, well, the fastest way to do it is to use your special right triangles. This would be 50, and this would be 50 radical 3. Now, if you did 100 times cosine of 30, comma sine of 30, and you might want to actually pause the video and do this, you would get 50 radical 3, comma 50. So that's exactly what we have. Okay? So let me see. Let me go back to, let's see. Let's go back to get our equation out for this, because you guys are not used to working with vector equations. So we're going to use this equation right here. Okay? So it says the final position. So R is a vector that represents position. It points to wherever our object is at any point in t time. Okay? It was the initial position function. Sorry, that's velocity. Excuse me. The initial position vector, which for us is just 0, plus the initial velocity, so what angle and speed it's being launched at, times t, and then we'll just write it like this for now, plus 1/2 times the gravity vector times t squared. Well, in this problem, let's see, our initial is 0, 0, okay? The initial, we said, was 50 radical 3 and 50. And then the gravity is always 0, negative 9.8. Okay? So, now remember, we got to multiply this and this by some t's, t and t squared. So our position function, which is a which is a vector valued function, will be this. Let's see. 50 radical 3, 50 times t, and then plus 0, negative 9.8 times 1/2 t squared. Okay? And remember, when we add vectors, we add the x values and we add the y values. So another way to write our final velocity, our final position function will be 50 radical 3 times t and then this one, the y coordinate will be 50t minus, so 9.8 times 1/2 is 4.9 t squared. Alright, so we are going to primarily look at this. Another way to write the final position vector function in general is then cosine theta times initial velocity t, v sine theta t minus 4.9 t squared. So we're going to need to that's the one I'm going to use the most often. Okay? Alright, so now that I've kind of established this stuff, if I want to know which one goes the highest, then I should probably just look at the y component of this function. So if I put that y component into my graphing calculator, let me clear these. I will get, for the first one, uh, 50x minus 4.9x squared. Let me graph that thing. Alright, that's what it looks like. I've already kind of fixed my window, which is why the last video wasn't very good. Now let me scroll down here. So if we had still had the 100, but now this was 45 and 45, our components would change to 50 radical 2 and 50 radical 2. So then our position function would turn into, come on, there we go. Let's see, it would turn into 50 radical 2 times t, and then 50 radical 2t minus 4.9 t squared. Alright, so now let's put that into our graphing calculator. The y value, So y equals, now we'll put 50 radical 2 times x minus 4.9 x squared. Let's graph that one. Ah, I see. So if we increase the angle, it's going to go higher and further. Okay, so let's do one more. What if we launched it at an even steeper angle? What if we launched it, down, down. What if we launched it at 60 degrees at a speed of 100? Well, now this would be 50, and this would be 50 radical 3, and our position vector function would now be 50 t comma 50 radical 3 t minus 4.9 t squared. Alright, let's put that in our graphing calculator. Y equals, let's go down one more. And we're just graphing the y, we're just examining which one goes the highest. 50 radical 3 x minus 4.9 x squared. Let's see what happens to this one. It goes the highest and the furthest. Interesting. Interesting. I like it. Let's zoom. Let's take my window and let's go up to 350 here. And now let's see that graph. There's the first one. There's the second one. And the third one. Okay. Alright, so I'm kind of surprised by that. I thought the third one would go higher but not go as far. And we'll have to figure out more about this as we go. Let's do one more example problem. If a cannonball is blasted at a 20-degree angle with an initial velocity of 300 miles per hour, what is the range of this cannon? So here, we're firing it at a low angle. 300 miles per hour. We're going to have to change that because gravity is negative 32 feet per second squared. So we need to change miles per hour into feet per second. Oops. Now I'm just all of a sudden changing to brackets. 60. Sorry. 1 minute has 60 seconds times, we need feet, 5,280 feet, and 1 mile. Feet per second. Okay, let's figure out what that is. So we got 300 times 5,280 divided by 60 divided by 60. So that's 440 feet per second. Okay. All right. Now we know that this is, so I'm going to change that to 400. Come on, ViewSonic. 440 feet per second. All right, so now, if I want to write the components of that, it's going to be, so let's see, our initial velocity is 440 times cosine of 20, comma sine of 20, and I'm going to figure out what that is by pausing this. I'll come back. Okay, so hey, I just popped those into the calculator. I just try to save you guys a little time to keep this video under 25 minutes. Okay, so this is our initial velocity vector. Our gravity vector is negative 32 feet per second squared, which is 0, comma negative 32. All right, and we are going to use, in this case, our position function, R final, is, let's see, can I get this right? It's going to be, let's go back to the last slide. V cosine theta t, okay, V sine of theta t minus 4.9 t squared. So, our final is going to be, too many, 413.46 t, comma, 150.49 t minus, not 4.9 now what's half of 32? 16 t squared. Now, this is the irony behind this. We want to know how far does this cannonball launch. That is x comma 0. So what we're going to actually do is figure out where this thing equals 0. Okay? So where is 150.49 t minus 16 t squared equal 0? When is our height 0? All right, well that's going to be t, let's factor out a 16t, times 150.49 divided by 16. Gosh darn it, 150.49 divided by 16. So 9.406 minus 1 t equals 0. So t must equal 0. Okay, that makes sense. Here, the height is 0 after no time, or it's 9.406 seconds. Oh, that makes sense. So, now what we need to know is at 9.406 seconds, how far to the right did it go? So I just multiply that number times 413.46, and the position tells us that at 9.46 seconds, we get the points 3888.8, comma 0. So the maximum distance this cannon can fire is 3,888.8 feet. Now, I beg you to fact check me on this video, Trump style, and tell me if I've messed some things up, because there's a high likelihood that I have. And if I did, I'll promise you I'll redo the video. Or if you want to redo it, you can redo it with me. But this is enough for you to get started, and I'd love to help you on anything you need help with on the worksheet that's attached. Boom!